Video game playing is becoming an increasingly popular pastime, and game developers are constantly looking for new ways to improve the gaming experience. In particular, there is much interest in applications of artificial intelligence and its uses within the video game industry. For example, creating more realistic enemies or friendly characters who play the game alongside you, which is the main motivation for this project, titled Using Genetic Algorithms to Train Neural Networks for Video Game Playing. A mouthful, I know. So let's break it down. Firstly, what are neural networks? Or more specifically, artificial neural networks? Put simply, they're machine learning models that take inspiration from the human brain to solve problems that are easy for humans but conventionally hard for computers. These models can come in many different shapes and sizes, called architectures, with the one used in this project being the multi-layer feed-forward architecture. This architecture works by taking in input from an input layer, propagating it forward using weighted connections through to hidden layers, which identify complex features in the input, and then finally propagating these features further to an output layer which produces the model's final outputs. This layer-to-layer propagation can be handily represented by this equation, which states that the vector of values for one layer is equal to the vector of values in the previous layer, multiplied by the weight and bias matrix of the connections between the two layers, all transformed by an activation function, which, in this project's case, is the relo activation function, simply setting a lower bound of 0 to the values. But how do we actually determine the weights and biases which will give us the output we want? Well, that's the job of training, which optimizes the neural networks to convert input to output for a specific task. Although there are many types of approaches to training, the one used in this project is neuroevolution, specifically neuroevolution using genetic algorithms, which is a training technique that takes heavy inspiration from the theory of natural selection and genetics, and contains 3 main steps: initialization, fitness assessment, and evolution. Initialization is the first step, which is done only once at the very start of training. It involves generating the initial population of networks to work with, usually each with randomly sampled weights and biases. This starting population is also referred to as the first generation. After this comes fitness assessment, in which each network in the generation is assessed and given a fitness value corresponding to how well they can complete a given task. In the case of video game playing, this fitness value could correspond to how well they perform when playing through a certain in-game level. Then, finally, comes evolution, which uses these networks and their respective fitness values to create a new generation of networks whom, in theory, should have evolved to be better at the given task. This process of fitness assessment and evolution repeats over numerous generations until the networks evolve to complete the task optimally. To better explain how this evolution step works, we can simplify it into 3 main stages, which are parent selection, crossover, and mutation, usually done in that order. In the parent selection stage, the networks which will be used to produce children for the next generation are chosen. For example, a simple approach to this would be to select the top 20% of networks based on fitness values and use them as parents. Then, during the crossover stage, subsets of these parents are chosen and combined to produce the child networks making up the next generation. For example, child networks could be created by randomly sampling weight and bias values from the chosen parents. Finally, in the mutation stage, each of the new child networks in the next generation are given a random chance to mutate. For example, if a mutation does occur, it could randomly shift some of the child's weight and bias values. The application of neuroevolution using genetic algorithms for game-playing AI has shown great promise in research and simpler games, such as simple 2D point-to-point car racing games and small arcade-style Atari games. Overall, it has been shown to produce performance comparable to, or better than, other more popular state-of-the-art training techniques within the domain of video game playing. However, despite this, it has seen relatively little use in commercial video games. Therefore, this project's main aim was to apply the technique to train artificial neural networks to play the first 4 levels of one of the most well-known and best-selling commercial titles, Super Mario Bros. To achieve this goal, the first step was to implement the game environment, which would handle running, sending inputs to, and retrieving outputs from the Super Mario Bros. Game. To run and send inputs to the game environment used a Python-based NES emulator, and to retrieve outputs from the game environment extracted and processed data directly from the emulator's in-game memory. One of the most important outputs from the game environment was the frame observations, visualized here. These observations were the inputs used by the neural networks to make decisions on which in-game actions to take every frame, and were designed to reduce the game screen down to only the essential components needed for optimal in-game decision making. The next step was to create the artificial neural network implementation, and the system which would use genetic algorithms to train them. During training, this system would act as an intermediary between the neural networks and the game environment, to allow the neural networks to play through levels and for their fitness to be assessed. This training system implemented multiple different algorithms for each of the previously mentioned evolutionary stages. To find which combination of these algorithms and other hyperparameter values gave the best training performance, a hyperparameter selection experiment system was implemented, which functioned very similarly to the training system. The first run of this experiment was used to determine the best combination of parent selection, crossover, and mutation algorithms. The results, shown here, indicated that the best combination to use was tournament parent selection, mean-based crossover, and greedy mutation. Then, the second run of the experiment was used to determine the best values for the other hyperparameters associated with this combination of algorithms, with the determined optimal set of values shown in this table. This set of hyperparameter values performed the best, reaching an average level completion of 68% after 50 generations. Finally, the training system could use these optimal hyperparameter values to train the final neural networks, which a demo system developed to showcase their gameplay, shown here sped up for the sake of this video. As this gameplay will show, the neural networks were successful in evolving from having zero game knowledge to having the gameplaying abilities to beat the first 4 levels of Super Mario Bros. However, not only were they able to complete the levels, but a self-run human baseline experiment showed that they were able to beat them faster than the average human, with their level completion times being consistently lower than that of low to medium experienced players on all levels, and the same or lower than that of high experienced players on all levels but the second. Furthermore, an ease of use survey was conducted, with the results showing that the training, hyperparameter selection experiment, and demo systems implemented throughout this project were all user-friendly and easy to set up and use. Therefore, these results show that neuroevolution using genetic algorithms is a more than viable training technique to use for commercial game-playing AI, and the ease of use of the systems developed shows that developers need little subject-specific knowledge to start using the technique to create AI for their games. These promising results are probably leaving you wondering why, as mentioned before, the technique has seen little use in commercial video games. Well, one of the main reasons for this is said to be the black box nature of artificial neural networks, which is a limitation stemming from the fact that it is very hard to distinguish what exactly was learned during training, making it almost impossible to fully understand the behaviour of the neural networks and how they actually reach their output decisions from their inputs. This is especially problematic in video games, where the developers need to be 100% sure no AI-controlled characters will deviate from the game's storyline. So, this project also aimed to reduce the impact of this limitation by implementing 2 different neural network visualization techniques. The first one you've already seen, which is a dynamic neural interpretation diagram, shown on the right side of the demo system, and the second is a simplified layer-wise relevance propagation approach, implemented into its own standalone system. Together, these systems can help give a better insight into the neural network's behaviour and decision-making process. For example, the mostly green positive connections going to the jump output action on the neural interpretation diagram shows that the network shown is likely to use the jump action in most situations. Meanwhile, if we select the jump output node in the layer-wise relevance propagation system, we can see, for example, that for this network, the green cells in the centre grid are where enemies would need to be to increase the chance of the jump action being chosen. To conclude, this project's main achievements were, firstly, proving the viability of neuroevolution using genetic algorithms for commercial video games by employing the technique to train neural networks which perform better than the average human on the first 4 levels of Super Mario Bros. Secondly, the ease of use of the systems developed showed that it is possible for game developers to harness the technique with little prior knowledge or experience. And finally, the implemented neural network visualizations explored how the main limitation preventing the adoption of the technique in commercial video games could be addressed. I look forward to seeing how this work could be built on in the future, and if the use of neuroevolution becomes more widespread in the video game landscape as the approaches discussed in this video are improved upon. Thank you very much for watching.